class, this is Professor Kamen with Machining 1319, and this is your video presentation for powder metallurgy. Now, powder metallurgy is probably a manufacturing process that you haven't heard of. Some of you might have heard of it, but it's not as old as some of the other manufacturing processes that we've been talking about, like casting and hot working and cold working. But it's essentially what it sounds like. You're making parts from metal powders. And this presentation is to teach you a little bit more about this manufacturing process. So let's get started. So ask yourself the question, what is powder metallurgy? It starts out, of course, with metal powders. And so there's different ways in which you can make metal powders. You can also make alloys, which are different combinations of metals if you want to. And we'll talk about that in the next couple of slides. But from that point, you mix together the metals or the metal powders needed for your alloys. Sometimes you have binding agents and sometimes you don't. After that, you have some type of compacting process. And this compacting process presses the metals together. This is a symbol of a mechanical pressing process, which is one of the most common types of compaction processes for powder metallurgy. After that, it's called a green compact or a briquette, because it's pressed together, but it's still in a weak form. Then it goes through what's called a sintering process. And during this sintering process, those metal particles diffuse together and all the pores or the spaces in between the powders get smaller and smaller. That happens during this sintering process. Then it's cooled. And then the last step, if there is a last step, includes secondary operations, which could be machining processes and other finishing processes before you get to your last part. So this is the basic steps in the powder metallurgy process. Let's look at a video that first talks about the basic compaction process, mechanical compaction.
Let's take a closer look at the compacting process. For the better you understand the mechanics of how PM parts are made, the better you will be able to take advantage of the benefits of this well-established manufacturing process. Typical compacting techniques use rigid dies set into special mechanical or hydraulic presses. Tool sets are made of either hardened steel and or carbides. There is a die body or mold. And for simple geometries, at least one upper and lower punch. And in some cases, one or more core rods, which will produce the designed-in holes if required. The die receives a charge of blended powder. The fill ratio of loose powder is around 2.5 to 1. This is delivered to the cavity by a feeder shoe. The upper and lower punches compress the powder. The upper punch is withdrawn, and the lower punch ejects the pressed compact. The feeder shoe, or transfer mechanism, takes the piece away from the die cavity. Then the feeder shoe refills the cavity with another charge of powder, and the cycle repeats automatically.
All right, and now let's continue on. So this is simply a diagram of the compaction process that you just saw. You have your chute here filled with powder, and it fills your cavity with powder, and then you have your presses come in. Sometimes there's a core to save the space for a hole or inner diameter, and then it's pushed out. The next process after the metal powder, making the metal powder, and then compacting is called the sintering process. In the sintering process, these metal powder particles are heated so that the pores or the spaces in between them get smaller and smaller. And this is called a diffusion process. This heating or this sintering occurs at a temperature that's below your melting temperature. Otherwise, the part would melt and it wouldn't meet the dimensional parameters that it needs to meet. So in the end, the goal is to get rid of all these small pores. Powder metallurgy can produce what's called net shape or near net shape parts, which means that the parts don't need any secondary processing. That's for net shape. Or if you say near net shape, it means the parts need very little secondary processing. So again, this is just a straight rundown of those basic processes involved in powder metallurgy. Making metal powder goes without saying, but the compaction process, when you take that loose powder and you squeeze it together in a die to form a briquette or a green compact. Then the sintering process, when you heat it so that the particles are joined by diffusion. Remember, they're not melted together. Okay, they're joined by diffusion, getting rid of those pores in the middle of the metal powders. And then secondary operations, if secondary operations are needed, they include things like sizing, machining, heat treating, impregnating. Lots of these things we'll talk about in a little bit more detail as well.
Metal powders used for parts production can be a combination of various elemental particles or pre-alloyed powder. If elemental powder is used, each of the ingredients that will comprise the desired part are mixed in proper proportion into a uniform blend. With pre-alloyed powder, the proper proportion of ingredients is already present in each particle. In either case, additives such as binders and lubricants are usually added. The powder is then consolidated in molds or dies, shaping and densifying it into a compact of the desired part. At this point, the part, or compact, is in a green state, where the powder particles are just lightly joined together. In this state, the parts have a so-called green strength, which is usually only sufficient for handling purposes. The parts are then transferred to a sintering furnace. During sintering, parts are heated at a temperature below the melting point or range of the base metal, but high enough to metallurgically bond the individual particles. Sintering further densifies the parts, increasing strength. Final part density is extremely important. Although controlled porosity is required and achievable for certain parts, the performance of structural parts increases directly with increasing density.
All right, now let's start to talk about how some of those metal powders are made. The first and most common type of way of making metal powders is called atomization. The basic atomization process is when you have a stream of molten metal, and this stream of molten metal is then turned into metal powders or metal droplets, and they're solidified typically by blowing either an inert gas or air or water across it, and that breaks up the metal stream and then creates some metal particles. This is an example of water atomization. As you can see, this is a water spray. Here you have the molten metal coming down, the water spray hits it, and then it breaks it apart, cools it, solidifies at the same time, and the metal powders gather together at the bottom. You have other types of atomization processes. You have the gas atomization process, and this process is the same thing as the water atomization process, except you're using an inert gas. Now, the reason that you do use an inert gas is because you don't want the gas to react to anything. Remember, this is molten metal, so it is pretty hot. And so you go ahead and spray an inert gas against it, and that breaks apart that molten metal flow into metal particles. One specific characteristic you want to remember about gas atomization is that it gives you more spherical type shaped particles. Another type of atomization, as I mentioned the first time, was water atomization. And water atomization, of course, the same process, but you use water instead of an inert gas. And one good characteristic about water atomization is that you can have more rapid cooling, and it's typically used for higher production rates. And the reason why that is because the water greatly cools down the molten metal and the particles at a much higher rate than some of your other atomization processes. Centrifugal atomization occurs when you pour, again, molten metal, and the molten metal falls on a spinning disk, and as it falls on the spinning disk, it cools and solidifies when it hits that disk, and as the disk is spinning, centrifugal force breaks apart that solidify molten metal and flings the particles out to the side. So that's centrifugal atomization. You also have rotating consumable electrode atomization. And what happens in this situation is you have a tungsten electrode, okay, and that electrode is broken apart by essentially by an electric current. And as it's broken apart by an electric current, it's spun to the outsides as well. Other processes that can be used to make metal powders include chemical reduction, which is a chemical process. And reduction really just means that you remove oxygen. So you start out with a metal oxide. That's a gas that involves a combination of metal and oxygen. And then you get rid of the oxygen, which leaves just the metal left over. And that produces more of a spongy and porous type particles. Now, we talked about how you produce metal particles. Let's talk about the next step, which is a compaction process. As I mentioned to you before, most common is the mechanical press is being used for the compaction process. This can be used for high production. You can also use a hydraulic press if you want to, but hydraulic presses don't lend themselves to high production because they can give you higher forces, but they're also very slow and have low productivity. So here again is another description of a compaction process done by mechanical press. See, here's the hopper again, fills with powder with just the right amount, then runs over the cavity, and then you have the presses come in, and here's a core in the middle. They compress together, and then they push it out, and something pushes it forward from there. Make sure we're back at the right place here. Okay. Now, there are other compaction processes other than just a mechanical press or hydraulic press. And one of the other processes is called cold isostatic pressing. I'm going to move this picture down here just a little bit so you can see a little bit more. I'm going to make myself a little bit smaller. All right. So that way you can see things just a little bit better. But the cold isostatic pressing process, what happens here is you start out with an elastomeric material or mold. That's kind of like made of some sort of rubber or a type of material that's very, very elastic, okay? And it's made in the shape of the product. And you fill that up with powder, and then around it, you put water or oil, and then you pressurize it. And as you pressurize it on all sides, move on to the next diagram right here. As you pressurize it on all sides, it compresses that powder together on all sides with an equal amount of pressure. That's what the ISO means. ISO means the same. Isostatic means the same all the way around. And so this is called cold isostatic pressing. The reason why it's called cold isostatic pressing because it's cold with respect to hot isostatic pressing, which we will talk about next. But this is done at room temperature, and it's done with either water or it's done with oil. You also have an example of hot isostatic pressing. This is a very similar process, but it's done with an inert gas like argon or helium. And it's also done at much higher pressures and much higher temperatures. Now, it being at much higher pressures and much higher temperatures allows a higher density that can achieve a finer microstructure than the cold process. So, as I told you before, these are worked at very high pressures and high temperatures, up to 15,000 psi and 2,000 degrees Fahrenheit, which is extremely hot. In this case, your mold or the shape in which you pour in the metal powders is actually made of like a thin sheet metal, as opposed to something that's kind of like a rubber type mold. And here's an example of this. Remember, the gas that you're using is inert as well, because you have very high temperatures and very high pressure, so you don't want the gas to react to anything. That's why you use an inert gas in hot isostatic pressing. And here's a video talking a little bit more about hot isostatic pressing.
Welcome to Sunbeak, a world-leading producer of near-net shape products produced by hot isostatic pressing, or HIP. HIP solutions offer many benefits compared to traditionally forged or cast products. Complex geometries, no pores or weaknesses, and short production times are just a few. HIP products for offshore operations, power generation, and other applications can be produced in a wide range of Sandvik grades. The manufacturing of metal powder for the HIP process is based on controlled quality scrap and alloying materials. Melting takes place in an induction furnace. The chemical composition of the melt is closely monitored throughout the process and adjusted to meet Sandvik requirements and international standards. The powder is produced by blowing inert gas through the melt, which solidifies into small spherical metal droplets. Rapid solidification of the melt produces a metal powder with a fine-grained microstructure. The metal powder is collected at the bottom of the atomizing tower. To ensure a consistent and homogeneous powder quality, larger particles are removed. Manufacturing of the finished component begins with the design of a capsule according to the required near-net shape of the finished product. The ability to manufacture HIP products with irregular shapes and complex geometry offers several advantages compared to castings or forgings. The capsule is made by forming and welding sheet metal. The tightness of the finished capsule and its welded joints is verified by testing with helium gas. The capsule is filled with metal powder according to a pre-calculated weight. The powder is packed by vibrating the capsule. After filling, the capsule is again tested for tightness with helium gas. The filled capsule is evacuated and inserted into a cylindrical hot isostatic press. This is where the hot isostatic pressing process begins. To obtain 100% densification, the capsule is exposed to high isostatic pressure using argon gas and applying high temperature. The volumetric shrinkage during the HIP process is approximately 30%. The HIPed material is heat-treated in qualified and approved furnaces to obtain correct properties. Rapid cooling is important for many materials to ensure the required properties are attained. After heat treatment and removal of any test material, the part is pickled by submerging the capsule in sulfuric acid, which dissolves the sheet metal. The HIPed material undergoes destructive testing to verify strength, toughness, corrosion, and structural properties. The final product is fully inspected for defects using non-destructive, ultrasonic, and dye-penetrant testing methods, as well as ferritoscope and positive material identification. The geometry is evaluated by laser scanning after the HIP process and before machining to verify that the product meets dimensional requirements.
Okay, so that video was a little in-depth about the hot isostatic process, hot isostatic pressing process. So another type of compaction process is called metal powder injection molding. And this process is actually very similar to the die casting process that we've seen already when we talked about casting. It's also very similar to the injection molding process that we've seen before as well. What happens here is you inject just powder. So instead of molten metal, you're injecting powder into these molds. And this particle size of these powders is going to be a lot smaller. But this has some very, very big advantages. And I'll move my picture up a little bit here so you can see. So this process allows very thin walls and high densities and some unsymmetrical shapes along with accurate dimensions. So that's some of the advantages of metal powder injection molding. oftentimes you will have some type of binder. A thermoplastic binder just means that it's activated by heat, but you'll have some type of binder that's in there when it's compacted to kind of help it hold together in that briquette before it's sintered. And here is just a quick video showing you that process. So here you have the metal dies that are holding the mold. Here you have the powder being sent in, and then this is the injector right here. The injector takes the powder, injects it into the mold. At that point later on, you're definitely going to have some secondary processes to machine off the pathway that it takes to get to the mold cavity. Now, another process of compaction is called powder forging. And this is actually a process that can happen after a normal conventional compaction process occurs. In this process, what you have is this briquette or green compact, again, goes through a normal press and then it's sintered, but then right after it's restruck or forged again, and this brings it to a final and increased density. So it brings it to a lot higher density than what would normally happen. And in this case, you can have very, very high mechanical properties, high fatigue, and impact strength, particularly compared to other powder metallurgy methods. Okay, so what are some other secondary operations that we have going on here? We have sizing, and sizing is when you force a product into a die that's very, very specific to the correct size, okay? And so it's meant to ensure dimensional accuracy. So that's a sizing process. You can have impregnation, which is where you put oil or some other liquid inside the pores of a powder metallurgy product. And an application of that would be pre-lubricated bearings, where the oil that's been impregnated, when the bearings get hot, the oil loses viscosity and comes out. When the bearings cool down, then it's sucked back in through capillary action. So that's just one example of impregnation. Then we have what's called infiltration. And in infiltration, what you do is you fill a powder metallurgy part, you fill the pores with another metal of lower melting point. The reason why it has to be a lower melting point is because this other metal is liquid metal. And if it's at the same melting point as your initial part, then your part itself is going to melt, which is what you do not want. And so remember, the infiltration process is where you take a metal, you heat it to its melting point, but that has to be below the melting point of your part, okay? And then that liquid metal is used to fill the pores of the metal in your part, fill the pores of your part. Other secondary processes would be more traditional, like machining, different machining processes, which could include grinding. That's considered a machining process. Things could also include annealing. So we talked about annealing doing cold working, so we could include that process as well. In addition with drilling and threading. For most pressing and compacting processes, drilling and threading is very, very hard feature to include. And so that's something that you really want to have as well. Okay. Well, that's the end of our video presentation. I hope it's been very helpful to you. Thank you very much.